Okay, welcome everybody. This is 60th Flow seminar, where Flow stands for Federated Learning One Word Seminar. And the seminar was created as a global online forum for the dissemination of the latest scientific research results in all aspects of federated learning. This includes distributed optimization, learning algorithms, privacy, cryptography, personalization, and many more. A few technicalities before we start. So this talk is recorded. And also, if you want to ask a question during a talk, please either post your question to chat or just raise your hand, and that's available through the participants menu. So for today, it's my great pleasure to introduce you our speaker, Amir Houmansadr, who is an associate professor of computer science at University of Massachusetts Amherst. His general research area is network security and privacy, with a particular interest in enhancing privacy on the internet. He obtained his PhD from the University of Illinois at Urbana-Champaign in 2012, and after that, he was a postdoctoral scholar for 2 years at the University of Texas, Austin, and he's recipient of many awards, including NSF Career Award, Google Faculty Research Award, and IEEE SAP Best Practical Paper Award. And today, he's going to tell us about poisoning attacks on federated learning. Thank you, Amir. The stage is yours.
Yeah, thanks for the extensive introduction. Hello, everyone. It's my pleasure to attend this seminar series. And today, I'm going to talk about poisoning attacks on federated learning. And most of the work I'm going to talk about is done. The credit goes to my students, Virat and Hamid, and also our collaborators, Peter and Daniel from Google. All right, let's get us started. So it seems like one of the key reasons for the popularity of federated learning is it doesn't make a strong trust assumptions between participants, right? So like it can be used for Google's Gboard, and I mean, literally there's zero trust between Android users, right? And therefore, this seems like the ideal technique to be used in such scenarios where the participants don't have any trust assumptions about the other participants. But this lack of trust can also be thought of as the Achilles heel of federated learning. Now, just imagine if an adversary, which we call the poisoning adversary, has somehow taken control of a number of these participants in federated learning. And now the goal of this poisoning adversary is to orchestrate the kind of compromised devices or the devices it controls to corrupt the global model that is trained during the training process by using them by instructing the devices to send malicious updates, right? So this is a type of vulnerability in federated learning, which is known as poisoning attacks, and there's been a lot of work. So today, my goal is trying to understand the significance and importance of poisoning attacks to production FL systems, those systems used by Gboard in other scenarios. The use of federated learning suggests that for financial services and banking and such, we're trying to discuss whether poisoning attack actually poses a real threat to these systems. So I'm going to start talking about some relevant threat models and types of attacks for federated learning. I'll show some performance analysis of federated learning in scenarios that we think are realistic settings and settings which match those of production FL systems. And also I'm going to talk briefly about some attack and defense strategies. All right, so let's.
Sorry, Amir. There's we have one question from Gaurav, so let me try and unmute.
Sure.
Hello.
Hey.
Hi. I just have a quick question. Do you define what is a production FL system, or is it more like a general guideline, like the scale of which Google uses or something like that?
Yeah, I mean, unfortunately, we cannot provide a definition. It's mostly I guess our perception of production FL is the consensus of experts or the understanding of experts in the field about what a production FL system is. But I mean, we can think of things that are deployed in the wild, like Google's Gbool. I think what we're mostly concerned about is the scale of their deployment and assumptions about kind of the fraction of adversary, the threat assumptions about these systems.
Yeah, okay, so the sense I get is at a scale, when there are like, when you're doing productions, FL at a scale. Okay, okay, cool.
Right. All right, so this is the outline for my talk. So I'll start by talking about some definitions and systemization for federated learning, poisoning, and then I'll talk about some attack and defense mechanisms. And finally, I'll give some evaluation results on scenarios that we believe represent production systems. All right, so let's start with the first part of my talk. So there's 3, or we can say 4 major types of poisoning, which I'm going to overview just quickly. So the first type of poisoning is what is called a targeted attack. And the goal here is that the adversary wants to have a certain class of inputs get misclassified into something else or into arbitrary kind of labels, right? So like, I guess the example you can think of is if you're messing up with, let's say, a driving assistant, I guess, FL application, then you want to have, let's say, stop signs misclassified as other things, right? So that's a kind of a targeted attack, but you don't care about other classes of input data. It's just some certain classes of data or even certain input samples, you want them to be misclassified into other things. Then we have backdoor attacks, which is kind of similar to targeted in the sense that you want to misclassify targeted input samples, with the difference that those target samples will contain some particular pattern, which is called the trigger. And the trigger could be a semantic pattern. So like in this case, in this picture, you see there's some kind of stripes on the background of those images, and that could be treated as the trigger that you want to use to kind of start the backdoor attack. Or it could be something semantic. It could be a white noise. It could be a weird signal on the images. And wherever that trigger exists, you want the machine learning, the poisoned FL model to misclassify that input class, right? So this is called a backdoor attacks. And finally, we have the class of untargeted attacks, untargeted poisoning, in which case the adversary doesn't really care about the input class. They just want to reduce the model's performance or utility on arbitrary input samples, right? So perhaps a good, I guess, scenario for, or perhaps motivation for untargeted poisoning is, suppose you're a competitor of Google, and now you want to reduce the performance of their Gboard app because you have a alternative and you want yours to perform maybe a few percentages better than their system, right? In that case, you would perhaps try to do an untargeted attack to reduce the accuracy of, let's say, Gboard on like arbitrary input sample. And so this is called the untargeted poison. All right, so now we asked the question of, when we think about FL systems deployed in the wild, which class should we be worried more about, or like which class of these attacks do you guys really think it's more important to, and could have more impact in practice? And there's no right or wrong answer. I mean, this is not to say that some of these classes of attacks are not relevant to production systems, but we would like to argue that untargeted attacks are, among all these classes of poisoning attacks, are the most important and the most potential, the class with the most potential impact on production FL systems. So I'm going to give a few reasons for this, and I'll I'd love to hear your kind of thoughts on this, and perhaps your suggestions. So the first reason we believe untargeted could be more significant is that when you perform an untargeted on an FL system, the model's accuracy will be reduced on arbitrary input samples. However, in the case of targeted or backdoor, it only impacts a certain class of input data. And in particular, in the case of backdoors, the input sample to be perturbed, impacted, even needs to contain a particular trigger in the signal. And in fact, this is what's been shown in the recent work that, so they define a factor, a metric called impact factor. And they show that existing work on targeted and backdoor, they only work for very tiny values for this impact factor. So like, for instance, an impact factor of 0.02 means that with 100 samples that the attacker has, they can only poison 2 samples of actual users. So the impact is, so you get to implement your attack on a very tiny fraction of actual samples in the practice, right? But that's the first reason. The second reason we believe untargeted is really important and it needs to be studied more is that we believe it's more difficult to be detected in the wild, and it can go for much longer before being detected. So in the case of targeted or backdoor, I mean, you can do some analysis and see that on some classes of input, your model's performance is significantly lower than the other data classes, right? And therefore, this could be used. And in fact, there's some prior work showing that you can use this to identify a kind of targeted attacks or backdoor attacks, right? But in the case of untargeted attacks, because you've reduced the performance on all input on all input classes to the same extent, it's really difficult to tell whether this low performance is because of an untargeted attack, or it's just because we don't have good amount of data, or it's just because this is a difficult task and we can't do any better, right? So the risk here is that it's possible that your model, your production FL system is poisoned with an untargeted attack for a longer time, and it may not be detected for a long period of time. Whereas in the case of a targeted or backdoor, it seems like with adequate inspection, it's possible to detect them at earliest stages of the attack. And finally, I'd like to say that untargeted are perhaps more challenging to study because it's a more difficult attack to implement, right? So because in untargeted, the optimization problem that you're trying to solve is to impact all input classes. So therefore, you can expect this to be more difficult compared to performing targeted or backdoor attacks. And in fact, this is the reason that I guess you see much better performances in backdoor attacks and targeted attacks when you compare them to untargeted attacks. So that could be one reason we see that they're more successful, because that's an easier problem to perform. Okay, any thoughts so far? Any questions? Any objections to my kind of claim that untargeted is perhaps more important than the other types? Okay.
No objections from my side, and I don't see any question from the chat.
I take it that was to some extent convincing. All right, so the rest of the talk is mostly focused on targeted attacks, and unless otherwise is stated, by poisoning attacks, I mean untargeted attacks. All right, so there's other so we've tried to perform a systemization of poisoning attacks on FL, and we've tried to understand different definitions and different attributes of poisoning attacks. I refer you to our technical report for further details, but maybe one last kind of terminology I'd like to explain is a distinction between data poisoning and model poisoning attacks. So in the case of data poisoning, you don't really have access to the device's internal operations, right? So let's say there are some Android users, and you've somehow managed to download some malicious data samples, labeled data samples, let's say, onto their devices. And now those kind of oblivious Android users, they use the data they downloaded from your malicious website to be used for training their federated learning application, right? So in that case, you're providing malicious data to perform the poison, right? On the other hand, the more a stronger version of poisoning is what is called model poisoning, in which case you actually own the device, or you've somehow compromised the device, and you're able to get into the internals of the app and like when your device is sending updates, you can actually pick and choose whatever malicious update that you want to set, right? So that's as you can expect, model poisoning can be significantly stronger because you have much more freedom in generating those malicious updates. But on the other hand, from a practical perspective, it's probably very difficult to obtain a large number of model poisoning devices, right? Because you need to either own them, purchase those devices, or somehow get kind of root access to those devices. All right, so there's other terminology.
Sorry, Amir.
Yeah, sure.
There's actually one question from Gaurav. Let me try to unmute.
Hello. So my question was on a previous slide when you said that untargeted attacks are harder to detect versus the targeted attacks. So I mean, if the accuracy is generally going down, why is that not a good metric to actually detect that there's something malicious going on? I mean, of course, there could be divergence in the data distribution, but I mean, at least it is a signal that something is going on.
Yeah, that's a great question. So I think the way I see these untargeted attacks to be deployed is that so the goal of the adversary is to reduce the accuracy or utility by only like few percentage points, right? So again, consider the scenario that you're a competitive Gboard and you want to have your next word prediction thing to outperform like Gboard, right? In that case, you don't really want to trash Gboard's performance, right? As long as your model is like few percentages more accurate than their system, you're going to be happy, right? And therefore, what we believe is the target of is the goal of untargeted poisoning is to reduce by a small amount, but on all input classes, right? And in that case, now again, so perhaps for some popular tasks like CFAR, I mean, the baseline performance, and if you don't get like 85%, you say something's wrong with the system. But for kind of proprietary applications and for unknown applications, when you get a performance of, I don't know, let's say even 93, you really don't know if this is the best you can do or if this is supposed to be 96 or 98, and now it's 93 just because of the poison, right? The difference is that in the case of backdoors or targeted, the goal is to reduce accuracy significantly on some input classes, right? Because again, so you have to think about the target applications, right? The objective of the attacker. So in the case of targeted, the goal of the adversary is your self-driving car misclassify a stop sign into, I don't know, a green light or something else, right? So you really need to reduce the accuracy on that particular input class. But I mean, if you like, I mean, and I guess one other thing is you can also do that for untargeted. So like you can try to reduce accuracy on all input classes by significant margins. But of course, that's not the type of attack we believe is practical because, of course, it can be easily detected, right?
Yeah, I'm just a bit confused because I mean, on one way you're arguing that the drop in accuracy is small enough that not to cause an alarm, but at the same time, the attacker is gaining sufficiently from actually doing from that small accuracy to have a competitive edge over the competition. So that it's sort of that is what is causing a bit of confusion.
Yeah. So again, the drop in accuracy could be just, let's say, a few percentage points, right? And that could be enough for the adversary, right? Like, I mean, like I said, you have to think about, again, from a practical perspective, if you put yourself in the shoes of the adversary, if your system is performing like 2 or 3 percentages better than your competitor, that's a win for you, right? But then the victim model, for them, it's probably not that easy to know whether this performance they're getting is what they're supposed to get, or if this is reduced due to some kind of poisoning attacks, right? And therefore, you could have poisoned the model for a long time before they actually figure out that their performance should have been stronger than what they're getting.
Okay. Thank you.
And again, so this talk is mostly, I guess, we're concerned about practical implications and real systems. So I think you need to consider these attacks in the context of real systems and like real world adversaries. What's the motivation for someone to do a poisoning attack, right? I mean, of course, right. So you have to think about what are the motivations for performing these attacks. All right. So let me skip these other terminologies. So now let's move on and talk about some attack and defense strategies. So the problem of poisoning has been known for a long time, on perhaps since the inception of federated learning, and the standard mechanism to defeat poisoning or Byzantine faults is that the server uses an aggregation rule, an aggregation mechanism to aggregate the updates that you receive from different devices. And the goal of this aggregation is that you want to reduce the impact of updates from malicious devices, but also you want to do it in a way that it doesn't impact the accuracy, the overall accuracy of your model, right? So there's different aggregation rules. And therefore, if you're an attacker, if you want to design a poisoning attack, your objective is to understand how the deployed aggregation rule works, and therefore design a mechanism to circumvent and bypass the mechanism used by that aggregation rule, right? There's different defense mechanisms. You can see them in this table. I don't want to talk about them, but each of them use a different mechanism, and each of them make different assumptions. And their goal is trying to single out potentially malicious updates or reduce the importance of those potentially malicious updates in the aggregation of all the updates, right? So here's the high-level intuition of a poisoning attack. Now, if you want to do a poisoning attack, there's a space of updates that is available to every device. And these updates are sent to the server. They're aggregated into the aggregate update. Now, the goal of the adversary here, if you want to design a poisoning attack, is to search within the space of acceptable updates and find instances or update samples, update vectors that have the most impact on the aggregate of benign updates, right? So it's you want to search within the space of like updates that is available to the adversary and find the updates with the most malicious impact. And therefore, and this is also very specific to different aggregation rules. So the space available to different for different aggregation rules is probably different, and also the aggregation mechanism is different. So the search space is different for different aggregation rules. So like as an attacker, you need to tailor it to different aggregation mechanisms. And therefore, this is an optimization problem, right? So recent works on designing poisoning attacks, they've done so by solving some kind of an optimization problem. So here's an example of model poisoning. So you see that here the goal is to find malicious model updates by maximizing the difference of the aggregates with the malicious update from the aggregate without malicious updates. And what we do here is that the adversary uses some benign data samples and tries to use stochastic gradient descent to move in the opposite direction of what it needs to be sent to the server. And then it searches within the space of different scaling factors of these updates, trying to find the most impactful value of that malicious sample, right? But again, there's some heuristics we're taking to solve this optimization problem. And similarly, I think you can do the same for data poisoning. So again, now in this case, your objective is to find data samples that when they're sent to the aggregation rule, they're likely to make the most impact on the aggregation of like updates from all the clients. And therefore, again, I don't want to get into the details, but this is another optimization problem. You try to find the most impactful data samples. And here's a pick at the performance. I guess I'll talk more about performance of attacks, but I guess this is slide, you can see that with increased percentage of compromised clients, obviously the performance of the attack improves. And also you can see that, so the red line is model poisoning attacks. Attack as expected, model poisoning can be significantly more powerful because it has much more flexibility in fabricating those malicious updates compared to data poisoning attacks. All right, so now let's move on and talk a little bit about defenses to poisoning. Any questions so far before I move on?
Yes, we have one question from Konstantin, so let me just unmute him. So please go ahead, Konstantin.
Thank you. So first question, does adversary have access only to a single device, or he can control more than one device? And in some sense, adversarial clients can collude.
Yeah, so I think we have to evaluate that attack algorithm with different ratios of compromised clients. So I think, yeah, so you can see this figure shows performance for different fractions of compromised clients, right?
I see. And adversary can control, so for example, we have 5 clients, and adversary has control over these 5 clients, or it's 5 independent adversaries which cannot collaborate to jointly poison them.
No, that's a great one. No, they can work. I mean, of course, the optimal way of performing the attack is that they also collaborate, because so these are attackers controlled by the same adversary, right? And therefore, the malicious updates that they send is performed and is generated in collaboration among all the malicious devices. It's not like they're independently sending malicious updates.
Thank you.
All right, so let me move on to talking about some defenses. Before talking about defenses, let's get back to this figure on how poisoning attack works, right? So like to do poisoning, there's
Sorry, Amir.
Yeah.
We have one quick question. So I guess that's relevant to the previous slide. So I just want to start. So it's a question by Elmer. So please, Elmer, go ahead and ask.
Hello, thanks for the talk.
Hi.
My question about the previous plot you had. So why do you restrict the number of compromised clients by 10%? Why it's not, say, 1/3 of the clients which is like Byzantine kind of thing, or it's not impossible here, or what?
Yeah, that's a great question. I mean, I'm actually gonna, like, in the rest of the talk, like later on, I'm gonna say that even 10% is too much for production systems. So like in the case of poisoning, again, so like this is not Byzantine fault resilience. This is kind of intentional poisoning attacks. So these are intentional, like adversaries that are sending malicious updates, right? So, and therefore, as I'm gonna kind of, I was going to talk later, parts of the talk, if we believe in a practical system, compromising more than even 1% of clients is not practical. So like think about like Gboard, right? That has like Android, like whatever, like it's 1 billion devices. Even 1% is like, I guess, 1 million devices, right? And now, and again, this is not about Byzantine fault tolerance. This is about intentional attacks, right? And the adversary, in order to perform the attack, you need to either purchase those devices and kind of introduce them to the system, or you need to somehow take control of those devices and compromise those devices, right? I mean, but of course, as you can expect, in increasing the percentage of compromised clients, we can expect increased performance of the attack. But we believe like even past 1% is not practical. It's not a realistic attack scenario. All right, so I guess.
Yeah, thank you.
Sure. All right, so let's talk a little bit about defenses. So here's the high-level picture about how we perform poisoning attacks. As you can see, the objective of the adversary is to search within some space of possible updates in order to find those instances that make the most damage to the aggregation of updates from different clients. So therefore, we believe that a nice mechanism to improve resilience to poisoning attacks is to reduce the space of updates available to the devices, right? So if you somehow manage to shrink the space of available updates, then you're limiting the adversary's choices in picking malicious updates. And also with a smaller space, it's probably easier to come up with better aggregation mechanism for updates, right? So again, this is a hypothesis that perhaps by shrinking the space of updates, it could help in improving robustness to poisoning. But there's also a catch. Not all shrinking of spaces are useful. So on the left side, you see that if you shrink it too much, it's likely going to hurt the utility. So because you're removing a lot of useful benign updates. And also it's possible that you shrink, but even your shrunken space contains a lot of malicious updates. And in that case, perhaps you've reduced the utility a little bit, but you still have you're still offering some malicious updates to the adversary, and therefore you're not getting much robustness. And in fact, there are examples of approaches in the literature that try to shrink the space of updates and suffer from one of these kind of two issues, right? Okay, so we've studied two directions toward this goal of improving robustness by reducing the space of updates available to devices. The first direction is using knowledge transfer by distilling the local devices model through public data samples. I'm not going to talk about this line of work, but the second line of work that I want to talk about is using ranking of gradients for shrinking the space of updates. So let me move on and talk about this mechanism. Okay, so the technique we're working on is called federated supermask learning.
Sorry, Amir, there is one question in the chat.
Sure.
So I'll try to unmute Sati.
Hello, thank you for the talk.
Hey.
From one of the Facebook's reports, it's known that, for instance, Facebook removed 6 billion fake accounts in 2019, which is more than all active accounts on Facebook. So it's safe to say that most accounts are on Facebook, for instance, are fake. So do you think if now we train a model on all data available on Facebook, it would be too much to assume 10% of them would be adversary?
I guess that's a great question. I mean, it depends on the scenario. So, I mean, and what particular application are you thinking about? I mean, relating to federated learning? So here's the other thought that we have in mind. So it's true, right? It's possible that you may have like a system may have a larger fraction of malicious participants or accounts or devices, right? But we believe that if a system has, like what you mentioned, if there's 10% or 20% of all the accounts in Facebook are Sybil accounts or fake accounts, then there seems to me a bigger problem with that infrastructure and with that system, right? There's probably bigger problems than federated learning that needs to be resolved, right? So like in the case of, I guess, Facebook that you mentioned, right? I think in that case, if I guess if there's, let's say, 20% malicious or fake accounts, in that case, there are bigger problems with the system that need to be solved. And therefore, we think that when it comes to federated learning for those applications, so does it make sense? I mean, if you have a system with like 10% corrupted users, right? So like, or let's say in a banking scenario for federated learning, if you are collaborating with like, I don't know, a bunch of banks and like 20% are trying to poison the system. So in that case, there's a bigger problem with the system, right?
Okay, makes sense. Thanks.
Right, but this is an intriguing question. I think right, or like if you think in the context of like Android devices, if like 10% of or even 5% of Android devices are compromised by an adversary, in that case, there seems to be a major issue with that system that needs to be resolved,
But
which is
the problem
beyond
is
just the problem of federated learning.
Yeah, but the problem is, I think it's not very difficult to run several Android accounts on a single device with virtual machines. So a single user can have so many accounts and there is no way to control this.
Yeah, but again, that issue is something that can ruin the ecosystem of Android, like in different levels, right? It's not just a problem with federated learning, right?
Yes, I also think this is a bigger problem.
All right, so let me move on and talk about FSL. I think we only have little time. So in federated supermask learning, the idea is that we try to reduce the space of model updates by sending rankings of parameters instead of sending actual parameter values, right? And this is the goal here is to improve robustness, but also, as you can expect, this also improves communication efficiency of Android federated learning system of the devices, right? So here's kind of the big picture. Like in the typical federated learning, what we're doing is that the server sends some updates or some the state of the global model, and the clients will send updates to those gradients. But in this case, the way it works is that at each iteration of training, the server sends some rankings of the gradients of the edges in your network. And then clients fine-tune those ranks and send back some updated ranks to the server, and the server aggregates those ranks. So this is how it works generally, but I'll talk about the specifics of how this is actually deployed and how it works. Okay, but again, the goal is that the kind of intuition is that if you use ranking, the space of ranks is a much smaller space than the space of gradient updates, right? So I guess it goes from, if n is the number of parameters in your model, if you're sending updates, the space is n times 32, if you're using 32 bits for each edge for each parameter in your network. But on the other hand, if you use ranks, it's n times log n, because you're just sending the ranking information. Okay, and the way we do it is we leverage a recent technique called supermasks. So this is based on a recent lottery ticket hypothesis that says if you have a big network, you can find a sub network within that network and train from the beginning on that smaller sub network and get the same performance. An extension of it is that you can actually start with a randomly initialized network, and instead of trying to train the weights, what you can do is to try to find a sub network of that huge random network that performs best for your task, right? So now the optimization problem to train a model is, instead of adjusting the weights, is to search within that big randomly initialized neural network and find a subset that is performing well for your task. And these are called supermasks, right? Now, this is the idea that we leverage to design our federated supermask learning technique. So here, this is how it works. It's first, we send, so at the beginning, the server uses a seed to create a random network, and also assigns random scores to each of the edges in the network. And the server will send the seed to all the devices, to all the clients, and therefore every device can regenerate that random kind of network, and also the scores locally on their devices. And then in each round of training, the server will send the global ranking at the end of that iteration to all the devices. Okay, so in each round, of course, as you can expect, now the clients try to fine-tune those ranks locally based on their local data. To do so, we're using an algorithm called the edge pop-up algorithm. It assigns the scores to different edges in the network and tries to see which edge from that random network has the most impact on the loss for different data samples. And therefore, you try to find it's kind of an algorithm to give a score to different edges in the network for your local data. And finally, each client will generate their own local rankings based on their local data. They send them back to the server, and the server will aggregate the ranking from all the devices by using, you can think of a simple voting mechanism to aggregate the ranking, right? So, and finally, that becomes the global ranking, which is sent to all the devices for the next round of training. Okay, so that's kind of, it's a simple technique, but again, the idea is that instead of trying to train weights collaboratively, the goal of FSL is trying to find the most optimal ranking of parameters of a network through iterations of federated learning. Okay, so I mean, as you can expect, this improves the performance of like the overhead of communications. It goes from n times 32 to n log n. So it gives some benefits on communication efficiency, but that's not the goal of FSL. So the big kind of objective of federated supermask learning is to improve robustness. As you can see here, when compared to other aggregation rules, it in fact has a promising performance on protecting the robustness of the model, right? So you can see that here, for instance, yeah, you can see the comparison with other aggregation rules and also with sinus GD, which is another technique for compression, but you can see that it doesn't provide, even though it's shrinking the space of updates, it's not providing robustness. And we actually do some, I mean, because we're dealing with ranks, it's actually quite easy to do robustness analysis. So we can actually obtain upper bounds on robustness, which I refer you to the paper for discussions and for the theoretical bounds on robustness. Any questions on FSL before I actually have one more slide to summarize FSL, but any thoughts or questions on FSL? Okay, so let me try to summarize the takeaways I'm trying to convey from the federated supermask learning technique. So we feel like space reduction is a promising direction to improve robustness, and we believe reducing like a ranking-based training is an interesting direction to shrink the space of updates and therefore improve robustness. Ranking has some nice properties, like training ranks has some nice properties. I mean, first of all, there are easy and strong aggregation mechanisms for ranks, which allows to further improve robustness. And you can also get other nice features with rankings. So like, for instance, you can use the ranks to personalize the models. So, I mean, this is, it can facilitate personalizing for groups of users and therefore improve fairness of federated learning. And also it allows you to unlearn malicious clients. So like with typical gradient-based federated learning, suppose that you find that client's number 10 has been a malicious participant, but this is like only an iteration number 100 or something, right? So like going back and removing the contributions of that client from gradients is really difficult, because I mean, essentially you have to go start from round one and kind of redo the training, right? But with ranking, it's much easier to unlearn a malicious client, because now you can, if you keep a history of the rankings provided by that client, we can try to aggregate those malicious rankings and try to negate the impact of those malicious rankings from the global model. And we feel like what we presented is perhaps a basic approach for ranking. We feel like there could be more effective and more complicated mechanisms for ranking and for ranking aggregation that future work can look into. All right, so
sorry, Amir, there is
yeah.
a question in chat by Gaurav. Just
Sure.
mute him.
So I was just curious. I mean, I saw this FSL using ranking to aggregate. Is it useful outside of just coming up with a defense against these attacks? Like in general, like if we, because communicating this is much easier in terms of communication costs. So like outside of this, is it useful or is it only in this context? This is
well, like I said, the big kind of objective of FSL or using ranking for training is to improve robustness, but as a side advantage, it also improves communication efficiency, right?
So so my question is, if you're training a model in a trusted network, right? But I mean, you do care about the communication costs. Would you recommend using it, or you think that there is you would still use the
Yeah, probably not, because as we show like in the paper, the overhead improvement or the communication reduction of FSL is not as kind of good as some other techniques for communication reduction. So like I think even Sinus GD is can do more compression on communication. So yeah, so if you're dealing in a scenario where you're not worried about trust, so perhaps this is not the best technique to use for compression.
Okay.
But like I said, it seems like it could have like the use of ranks could have some promising features that can be used to facilitate things like personalization and also unlearning, right? I mean, unlearning is an intriguing topic, and it's I mean, the techniques that exist, like dealing with standard federated learning, unlearning is not really that easy. I mean, it's not that efficient, but it seems like with ranking, it's actually quite more possible to do unlearning again in scenarios where that's what you need to do. Okay, so we have like 2 minutes.
I mean, we started past 5, so at least 8.
Okay. All right. So let me go quickly over the last part of my talk, which is some evaluations on for production FL systems. So I mean, first of all, I talked about these attacks, and I mentioned that we feel like untargeted is the most impactful for production FL. And I was asked this question of what do you mean by production FL anyway, right? And again, production FL are kind of our definition is any system that is deployed in the wild. It has a large scale of participants, and it's also concerned with real-world threat assumptions and adversary assumptions, right? So I think, as you know, there's 2 scenarios, and for each of these, we can, for each of cross-device or cross-silo settings, we can think about examples of production FL systems. So we have a draft that we're trying to evaluate the performance and significance of federated of untargeted poisoning attacks in particular for production FL systems. So we have some discussions in the paper. We argue that a lot of the assumptions made in the literature on evaluating untargeted poisoning on FL deviates from what we should expect from production systems. So like, for instance, I think one point that we talked about a lot, I think, throughout this talk is the percentages of compromised clients. I think, like it was mentioned, I think a lot of people believe that they should consider large percentages of malicious clients. And in fact, many of the existing attacks, many of the existing poisoning attacks perform very well only for large percentages of malicious clients. But we argue that, in fact, those are not what represent production FL systems, right? And therefore, so in this, we've done some analysis with parameters that we believe represent real-world deployments of federated learning. And we also try to narrow down the threat models. I mean, we try to search with and discuss all possible threat models with different features and try to identify those that we believe are relevant to production systems. So I'm just going to briefly talk about some results of our analysis that, again, we try to do using parameters that we believe represent real-world systems, real-world federated learning deployments. So the first thing is that when you implement these attacks for the set of parameters that we believe represent production systems, the performance of the attacks start to fall rapidly, right? So I guess with things like 1%, even with 1% compromised clients, you see that most of the attacks do not show much of an impact, even against simple defense mechanisms. And therefore, we believe this is important because now, in order for your defense mechanism to be deployed in the wild, you need to convince, let's say, Google or Apple or I don't know, whatever, that there's a big risk, there's a big threat to your system, and therefore you need to take the extra costs and perhaps added overhead to your system to deploy that defense mechanism. And we feel that existing attacks do not convey that message to, I guess, practical players in the field of federated learning. So I guess that's the first, and again, this is perhaps a matter of debate on what exact, what fraction of malicious clients is practical or realistic in real world settings. But again, at least in many settings, you can assume that large values are not what we can expect or what the players in the field believe or expect from the attackers to happen. We also see that despite there exist sophisticated aggregation mechanisms, we see that, again, once you analyze your system with the set of parameters that represent production systems, we see that even the simplest defense could be enough. So like, for instance, in the case of data poisoning, we see that if Gboard just limits the contributions from each client, that should be enough to protect against data poisoning attacks, right? And I mean, again, in the literature, we have designed a lot of sophisticated defense mechanisms, but we feel that in many practical settings, they may not be even required. We see that even when your attack doesn't work for those settings, it doesn't matter how long the system is poisoned, right? So like if your not making an impact within, let's say, 1,000 rounds, it doesn't matter if you go any longer. And finally, we have, I guess, similar analysis for cross-silo. Again,
Sorry, Amir.
Yeah.
There's one question by Constantine, so let me just unmute him.
Thank you. I would like to ask how malicious clients are modeled. So you present benchmark results. So these malicious clients, do they just produce some random updates from some distribution, or this is some sophisticated system, I don't know, driven by reinforcement learning or control? So how do you model these malicious clients?
Yeah, you mean how do we pick the malicious clients, or
No, how they behave? So what they produce?
Yeah, so we use we actually, I don't know if I have, yeah, so I think if you can see here, we try to evaluate against the existing state-of-the-art attack. So like each of these lines represent one of the existing attack mechanisms. So if you recall, I for instance described that optimization kind of based poisoning attack, like I guess a couple of slides earlier. So, but then each of these lines are from a different paper, and each of them represent kind of a state-of-the-art attacks that we know.
I see. Thank you. Oh, and just very fast question. So these experiments, where did you carry them? Does it exist any federated learning system that assist experiments with malicious agents, or you during creating this work you re-implement these papers, or like TensorFlow Federated allow to model this?
Yeah, so I think if I understood your question, so I think some of these we re-implemented, and some of them we got the code from the respective, I think, papers. Was that your question?
Yeah. But the question was like, does it support it natively by, let's say, TensorFlow Federated, or no?
Yeah. So our implementation is, yeah, it verifies with the results from like previous work, right? But I guess that the difference here is that we're evaluating for a different kind of set of parameters for the system than those systems. But if you use, we could reproduce the results from those papers if you use their set of parameters, if that's your question.
Yeah, kind of. Yeah, thank you.
Okay.
Thank you very much.
All right, so let me, I think we're out of time. Let me summarize, and maybe there might be some more questions. So I think the summary is that, I mean, poisoning could be quite impactful for different scenarios where federated learning is being deployed, and given the increasing use of federated learning in different systems and different environments, seems like it's an important area of research related to federated learning. We believe that existing defenses should consider the unique constraints of production systems, and they need to tailor their kind of defense mechanisms to the constraints of these systems. And then finally, like, as you know, there are other issues with federated learning, privacy, fairness, and therefore it's really important to see the implications of techniques that improve robustness on these other issues, such as privacy and fairness. I think with that, I don't know if we have time for more questions, but this is also, I guess I'll stop here to see the relevant papers.
So thank you, Amir, for your excellent talk. And I think we can, you can still take some questions. I mean, even though we are a bit over time, so whoever needs to left, just feel free. So, and anyway, we post the recording to the YouTube, so it should be all right. So in case you have any questions, just please raise your hand or just post your question, and then I'll try to unmute you. So yeah, maybe I would start with one question, or maybe like a comment. So you are talking with respect to like adversaries, that like how many, like what's the percentage of adversaries clients, but especially like in production, when you have like, you have to like, when you kind of select your clients, for the clients for specific communication round, they have to be like, for cross-device federated learning, they have to be connected, let's say, to charger, and they have to be connected on the like fast internet. And with that respect, like they actually the number of available clients, it's much less than actually the number of clients that there is overall. But this, I don't suspect this to be case for adversaries. So even like if you have let's say like 0.1% of adversaries, that effect of that can be something like 10%, just because they're always available. That, so whether you can comment on that.
Yeah, I think that's a great point, right? I think there are things that an adversary can do to amplify the impact of its available devices, right? Yeah, but again, I think this is an issue that is not just limited to federated learning, right? So like, I think whatever thing you're doing from the devices of those applications, you need to use better selection mechanism, right? Of course, it can also impact federated learning, but again, if you have a kind of crappy algorithm for selecting devices, there seems to be big issues with your design that you need to fix, which goes beyond just the problem of federated learning.
Thank you.